ELE 112, Chapter 19, Filter Theory. As you can see in the slide, we're going to be going over low pass, high pass, band pass filters. We might dabble a little bit into the band stop filters as well. This is your second introduction into filters. We've already looked at some of these pictures and talked about these ideas in chapters on 16 and 17 on inductors and capacitors. As you recall back in those chapters, low pass filters, which is the first one we're going to attack here. Low pass filters pass low frequencies. So what you're looking at is a frequency response curve to the right. This box here contains the resistor and the capacitor in the circuit. And as the frequencies come in, 1 and 2 and 3, let's pretend that we have two frequencies coming in that are to the left of the critical frequency, which we discussed in 16 and 17. Let's say that F3 is coming in way out here. Well, F3's clear out of luck, because at the output here, we would find F1 coming out and frequency 2 coming out. F3 would be attenuated. So if we were looking at a sine wave, F1 would come out, F2 would come out, and F3 would be extremely small coming out of this filter. And that's what a filter can do for you. It can remove frequencies. And there are times where, we want to watch channel 5, not channel 6 and channel 4 at the same time. We want to be able to filter out what exactly we want to enjoy. Here's this magic spot. We're going to learn in this chapter how to calculate exactly where the cutoff happens. Now, that doesn't mean that it's not working in this green area. It realistically is still working. It's just really, really attenuated. Really, the signal is gone for all intents and purposes. It's not quite at zero way up here, but it's on its way to death. Okay? So everything in the gray area is passed. Everything not in the gray area is reduced. And we called this the half power point. We called this the 0.707 point, 70% point. We called it the minus 3 dB point, whatever that dB is. We're going to learn about the minus 3 dB here shortly. Okay, so, if we're talking about low-pass filters, low-pass doesn't mean low frequency. It passes low frequencies, but what do you consider a low frequency? In different areas of electronics, different frequencies are considered low. 1 megahertz in cell phone industry, I'm sure, is considered a low frequency. So, you've got a 0 to 1,000 hertz signal here, and you've got another one, another low-pass filter that passes 0 to 100K. These are both low-pass filters. They start at 0 and pass 1,000. The second one starts at 0 and passes 100,000. They're both low-pass figures, okay? Low-pass filters, sorry. Now, what you're seeing here is a heads up on how to choose the actual crash and burn spot, the 70.7% or the 0.707 point, or the half power point, or the minus 3 dB. The minus meaning that the signal has gone down from 100% to 70%. That's a drop. So this is the equation. It's just 1 over 2 pi square root of the resistor and the capacitor. They both have to be metricless. They have to be, the resistance has to be in ohms, the capacitance needs to be in farads. More on that shortly. Back. Well, you know what? Hang in there for 1 second. I'm going to look something. I'm going to look at something here. Bear with me. Yep, they screwed up the formula. There is no square root in this formula. So I want you to go back here and make a correction on slide 3. There is no square root in that formula. Okay? All right, let's continue with our... Okay, so let's go off and talk a little bit about decibels, otherwise cryptically written as dB. Decibels are important in filter theory. They have no unit, and that's because you have divided usually a voltage by another voltage, and volts are in the unit of volts and they cancel. So this is a ratio. This decibel will be a ratio that we take and apply to a logarithmic formula. And it's used, as it says here, it's used to relate the response of the human ear to sound intensity. Now, if you were listening to a guitar amplifier and the output was 1 millivolt, and you were listening to another guitar amplifier and the output was 100 millivolts, you might think the 100 millivolt output is louder. It's definitely bigger. It's bigger in terms of voltage. It may or may not be louder. Depends on how your ear handles 1 millivolt versus 100 millivolts. So the decibel is used to provide a ratio of one of several things. One of them is voltage. Do I want to compare two voltages? If I get two voltages and I compare them as a decibel, and there's an equation coming, of course, then if your number is 1 dB or greater, you probably can hear that difference. It goes back to this area here where, the human ear, how it responds to sound intensity. So it's a ratio of two voltages. It's a ratio potentially of two currents, although we won't be talking about that. And it's a ratio of two powers. We also won't be talking as much about that either. We'll be talking about voltage. So you can kind of pack this equation away because we generally won't be using it. We will be using the voltage version of it. And what it does is it shows that the dB is a voltage ratio of what the filter provides on the output versus what you sent in. And the complete formula is 20 times log of V out over V in. And this requires a little bit of explaining. This bracket that you see here is not, I repeat, is not a multiply function. You have to take V out, which might be 5 volts, and V in, which might be 3 volts. Well, bad choice. Yeah, we can do that. And you have to plug those values in here and evaluate the log of 5 over 3, and then multiply it by 20. So there is a little multiply sitting right there in the logarithmic equation. Okay, so in your homework, you'll have to run a few of these and plug numbers in and see if you know how to handle it, etc., etc. Now, as we said, it's a logarithmic comparison of or measurement of one voltage, power, or current to another. So we're not going to compare voltage to power, power to current. We're going to compare two voltages or two powers or two currents, basically. Okay? Now, as I said earlier, the humans have logarithmic hearing, and we can detect changes as small as 1 decibel. That's why I said if you run this equation and you get like 3 dBs, you definitely can hear that. That's a sound change that is 3 times larger than what you were listening to. That's an amplified signal. Now, if you get a dB of minus 3 dB, this indicates, the negative indicates you have a loss. That means you put in 10 volts, you got 4 volts out. That's a loss. Now, maybe I should say something about that. Every circuit we do in this class will lose voltage. In other words, we'll build a circuit, all right? We'll build a circuit, we'll feed a frequency in, and we'll feed a voltage peak to peak, maybe 10 volts. The output will always be less than 10 volts peak to peak because we're not building amplifiers in this class. We're building just straight low pass, high pass, and band pass filters, and we have no power supplies. These are not what they call active circuits, okay? They are passive circuits, meaning that the resistor and capacitors are not powered. There is a voltage peak to peak going into them, that is true, but there is no voltage powering like you might have with a transistor or with an operational amplifier. So, more information than you might have needed, but good information. Okay, the decibel is used in filters to design filters and compare outputs to input relationships. People want to know if a frequency is fed in, what is coming out. They want to know what kind of filter it is, where the cutoff is, how many volts happen before the cutoff at a certain frequency, how many volts happen at the output. They want to know how quickly the filter is dying or killing or squashing the signal. Now, the other advantage of using a dB right here in yellow, the dB helps make all voltage and ratios size independent. And what I mean by that is I could have a box with a 10 volt. I could have a box with a 1 volt. With a 1 volt. Let's do this right. We'll do this for Eric, who goes by Mark in this particular version of the cartoon. We'll do this for him. So let's go back to the drawing and we'll put in 1 volt and we're getting 10 volts out, peak to peak, RMS, whatever you want to call it. We put a frequency in and we get more out than we got in, which is not going to happen in our circuits, that's for sure. But down the road it could happen, okay, in future courses. This is a ratio of 10 to 1 right here. The input versus the output, or the output versus the input. So it's going to be V out over V in, which is 10 over 1, a ratio of 10 to 1. If I put in 10 volts versus 1 volt, and I get a ratio of 10 to 1, and I decide to go with 100 volts and 10 volts, coming out is 100, going in is 10, it's still a 10 to 1. If I decide to feed the filter 10 k volts and my input is only 1,000, that's still a 10 to 1. The dB ratios don't care what the actual voltages are, only that their ratios are identical. So if you were to put this through a circuit and you could hear the difference, you should be able to hear the difference for all of these if they're greater than 1 dB in difference. Okay? So, very interesting discussion on decibels. Go journey here. What else? Let's see. What else we want to talk about? Let's talk about the dB, because it's used in what's called a Bode plot to view voltages versus gains. You know, so when we make this plot, which I'm about to draw, when we make this plot for a low-pass filter and it cuts off at a certain spot, the dB will be in this region here, replacing voltage, and your frequencies will be down here. This is called a Bode plot. For every frequency, there is a matching voltage. Whether it's dying, whether it's living, there will be a matching voltage. And we compute this scale by plugging it into the dB formula, not the actual voltages. Now, could we use the voltages? Yeah, we could. But we're going to do Bode plots, frequency versus voltage outputs. We're going to show the filter behavior and what happens with V out and V in. More is coming, so stay tuned. All right, so there's another peek at the actual frequency that is a low-pass filter that you're looking at right there. And I am trying to find some missing paperwork while I'm here and going blind looking for it, which is very interesting. Okay, all right, we'll get to it when we get to it, I guess. All right, so there's a picture of a low-pass filter. It's got the capacitor going down to ground, as you can see. That's where the capacitor has to be for it to be a low pass. Remember, this component has this formula. This is the most important formula for the capacitor. And it's a fraction, okay? I'm going to simplify the fraction. You see, if x gets bigger and bigger, the result gets smaller and smaller. What does that have to do with x sub c and x sub L and all that good stuff? Is that for the capacitor, it's the 1 over formula. This is not I, this is a 1. And as the frequency grows, resistance drops. As frequency goes up, x sub c drops quickly. It drops quickly, especially after the critical frequency spot, f sub c. So, you know, at low frequencies, this thing here is just a monster here. It's just huge. And I'll draw a picture down here. Here's what the capacitor looks like at DC going in, okay? There's the DC going in. The cap is infinite. So where would this voltage here go? All of it would go to the capacitor. So at DC, a low-pass filter passes everything to the output. But then as the frequency goes up, this thing starts to turn into a high wire short circuit here. And you know what the voltage of a short wire is? The voltage across a short wire happens to be 0. If you couldn't answer that, you would have had trouble understanding what I just covered, possibly. Okay, the output on across a short piece of wire, which has no resistance, okay? V equals IR. If I have 0 here, my voltage is also, you guessed it, 0, okay? Down below is the formula for calculating the critical frequency. I think I gave it to you wrong. I think I did. I gave it to you wrong in the first slide that we looked at back here. There it is. This is the formula that is actually correct. Write it down on your formula sheet. This one in red up here. This is a two-part component, two-part circuit that is guaranteed to give you minus. All right, next slide. The term roll-off is introduced. What you're looking at here is called a Bode plot. You're used to seeing it with the slide drawn this way. Okay, they've just taken the axes down here and moved it to the top, and it shows the circuit diving or losing voltage when it goes past the critical frequency, or the minus 3 dB point, or the 0.707 point, or the 70% point. This term roll-off, the pattern that you're seeing, the decrease, is called roll-off. And the roll-off is consistent. The circuit decade, let's rub that out. The circuit dies at a rate of minus 20 dB per decade. That requires a little explanation. First of all, a minus in front of a dB means signal loss, and we know that this filter, the further it goes beyond the critical frequency, which is right here, the further it goes, it's dying. There's a slope to this dive, and it's not a perfect straight line, but it is pretty straight. So minus 20 dBs, that's over here on this, between a change of 10 in frequency. That's a decade. So if I go from 1 hertz to 10 hertz, that's a decade. If I go from 10 to 100 hertz, that's a decade. If I go from 100 hertz to 1K, you got it, that's a decade. If I go from 1 megahertz to 10 megahertz, that's a decade. So what they're telling you is that with each decade or change in 10 of frequency, this slope is on an aggressive path down. Now, minus 20 dB looks really good until you ask yourself, well, is that really what you want from a filter? And the answer is pretty much no. What you'd rather have from the filter is a cutoff that drops at a given frequency. So, in other words, let's say this frequency is at 1K, then anything below 1,000 passes, anything over 1,000 dies very quickly. But what happens is the filter leaks. And it leaks at minus 20 dB per decade. This is a constant, guaranteed amount if you're using a resistor capacitor circuit, like 20 dB per decade of die in the signal. That's nice. It might not be the green box over here. It might not be this green box nice. It's a little bit sluggish, which means when you're trying to cut off at 1,000 hertz, you might get 1.1K, 1.2K, 1.4K bleeding into your circuit, which is not always a bad thing if you can tolerate it. Here's a professional Bode plot laid out on what's called log semi-log paper. Log semi-log paper. And if you want to get some of this, it's available free online. I would just Try to find something that's very similar to what you see. And what you've got here in this log semi-log paper is as I said, you're used to seeing this scale on the bottom, as you see here. And this is an undedicated set of values here. You can assign anything you want. What they're doing here is going up in decades. See, that's a decade, that's a decade, that's a decade. And, usually when you're talking about decades of frequency, not a lot changes sometimes between decades. So in an attempt to compress your circuit, to give you a chance to see this critical frequency and a little bit around it on both sides, they compress the frequency scale down here in blue check marks. They compress it. So we go from 10K in this plot all the way to 10K, from 10K to 10,000 kilohertz, sorry. And you say, well, why do they start this? Why do they start this at 10,000? I'll tell you why. What kind of filter are we looking at? We're looking at a low pass. Do you really expect that this portion of the line drawn in yellow right here, do you really expect this portion to change at 1,000 hertz, at 100 hertz, at 1 hertz? In other words, at frequencies below 10K, and the 10K is right here, right? So at frequencies to the left of this curve, this thing's just a straight line. There's nothing interesting happening. As a matter of fact, once you get through the drawing of the curve, as you see before you here, and we're going to go through and we're going to draw some of our own curves later on just to see how it's done. Normally you would have had a lab and had a chance to practice this. Once you've got this snippet of the curve right here and a little bit here, these points all fall on the minus 20 dB per decade path of decline. So there's no real reason to sit there and look at many, many, many more points. We can just take this line and actually extend it down here at a consistent rate. Oops. All right, so let's look at something very interesting. Here we are at 100K. And to get to 1,000K, all right? What is 1,000K? That's a megahertz. And so to go from 100K to a megahertz, that's a change of how much? How much? It's a decade, right? It's a decade. Decade. I want you to take a look at what your dB reading is here and what your dB reading is here. What's the difference between 30 and 10? 20. It's actually minus 20 dBs. The difference here is minus 20 dBs per decade, as I predicted would be the case. So that line, once it hits this red spot right here, or black spot right there, is pretty consistent all the way through that straight line that's drawn there. I mean, you can take a ruler and just draw a line, because that's what your resistor capacitor network is going to provide you in terms of performance. And yes, this is performance, because we don't really like this line. We like it to dive quicker. We like it to dive quicker, dive quicker. We would like it to be the green line straight up and down at 90 degrees, okay? But that's not happening with a resistor capacitor. I mean, you can't build a circuit that turns on and off on a dime like that. You're always going to have something that's going to give. So that's not going to be perfect. So all we can hope for is the best. I want you to take a look at, can we get away with it? We can't. This is the only place we can look at that. Let's see. Let's go from here to there. And I think we're at about 15, minus 15 dB. I think we are. And I think we're at about minus 35 dB here. What's the difference between 15 and 35? Minus 20 dB per change of 10 in frequency. Now that is 200 kilohertz, and this is 2 megahertz. It's the same as 100K and a megahertz. It's the same, okay? Now, what kind of circuit are we looking at right now? We're looking at a low-pass filter. Guess what? Same results with high-pass, same results with band-pass, same results with notch filter / band reject. The same kind of stuff happens. This roll-off that you're looking at, we're going to see it again. We're going to see this again in high-pass and band-pass as well. Okay, here's a low-pass filter, but it's built with the resistor over here, and to get away with that, we have to throw the inductor into the equation for it to work, and we need a different equation for the cutoff frequency. I'm not going to dwell on this too much. I'm just going to tell you that at very low frequencies, the inductor is nothing but a wire, not an open, a wire. So if I put 10 volts in, I get 10 volts out. I put 20 volts in, I get 20 volts out. See how that works? Now, as the frequency rises, the inductor chokes and starts to develop voltage across it, and steals from the output. And that's where you start to get the roll-off at minus 20 dBs per decade. Now, run off at some point here after we're done. Run off and try to teach your goldfish how to look at these things. Talk to your goldfish about roll-off. Talk to your pets. See if they like what you're teaching them. Enough not said. Notice that this equation is not LR. It's 1 over 2 pi L divided by R. So you're going to have to do a little division to get this thing to work. Okay. Oh. All right. Last 3 slides. These are problems that you need for homework. And I'm going to tell you right off the bat that I started off on a bad hair day today. And I put this square root in here that migrates its way through here and produces the wrong information. So what I need to do is scrap this problem. You're going to have to just work it without the square root in there. You will not have to square both sides. You'll be able to solve for, here we go. We're trying to get the capacitor, right? So I'm going to give you the answer right here. C is 1 over 2 pi F C. Let's see, what am I doing here? Yeah, C is RC, R and FC, R. There we go. Okay, this is the equation that you're going to need in your homework to solve those kind of problems. Now, I was smoking something bad when I was working this, and I didn't check my stuff. Basically, F sub C, which is 1 over 2 pi RC, you multiply both sides by RC. Actually, you don't even have to do that. You can just multiply both sides by C. Okay, so I'm going to take that back and make it easier. Multiply both sides by C, and you end up with FC times C is 1 over 2 pi R. Alrighty, see that? Now, you need C by itself, so we divide this side by F sub C and this side by F sub C. And this is where the magic happens. 1 over 2 pi divided by F sub C over 1 needs to be converted to a multiply by flipping this, producing, and I think I've left the R. What did I do here? The R. 2 pi R. I left the R out. So once you do this multiply, you end up with the formula that I suggested you would get up here, and that's what you plug your numbers in. So these are bad answers, okay? But you get the idea. You can solve your homework by doing it the right way. This problem is because I'm probably 15-20 minutes into page number 2. Okay. Boy, oh boy, I can't find my stinking stuff if my life depended on it. Here we go. Okay, low-pass filters. Here we go. There's a circuit. I'm working through some of your homework here. There's a circuit, low-pass filter circuit, where you've got the X sub C of 1,000 ohms and a resistance of 4,000 ohms. Find the output voltage. So, at this point, holy smokes, this kind of a problem should be on your hit list. This is just a problem with two components, and voltage divider will set you up. You're trying to find the voltage out here, given that you've got all the impedances and all the voltages, and that's an easy voltage divider thing. Did we have to? No, we could have used Ohm's law too to do this circuit. You would have had to get ZT and then go get IT, and then you could have found what the V out would have been after that. Maybe you try that to see if it works, okay? All right, second problem down here. It says calculate the decibels. Given that I have given you two voltages, 2 volts in and 2 volts out, which means no gain. Go ahead and calculate, drop them in here, and do a 20 log of 2 over 2. You'll find out that your decibels is 0. 0 indicates that it doesn't mean you have nothing. It means that what you put in is what you get out of the filter. So here you go. You fed 2 volts in. You got 2 volts out. That's a beautiful thing. No gain, but no loss. Run the computation again with 10 over 6, which means your output dropped, which is what we get with an RC type circuit or an RL type circuit. And your decibel actually drops, and you should have, I'm going to add a negative sign in front of that didn't make the cut. So I'll fix that on my master. Now, if you want to know why I didn't rework this slideshow, and holy crap, I mean, this stuff takes forever to do, so I just didn't want to have to repeat the world for another 20 minutes. I'm already swamped with all this high-tech stuff, laying out this new stuff for you. Okay, another problem here. Number 2. They want to know what the output voltage for this low-pass filter frequency is, given the input is 10 volts. Now, this circuit's a little different because they didn't give you the resistance of the cap. They gave you the microfarads. So you have to go off and run your own calculation here, and then you substitute this into the top of the voltage divider, and you get your voltage. Very straightforward. If I wanted to find the critical frequency, I could, but again, I'm going to tell you I got the wrong formula here, you need to get rid of that square root, and that's obviously going to give you a different value here. But while you're doing your homework, they're going to ask you to make this calculation, and you might as well as have 1 over 2 pi RC written down correctly on your formula sheet. Okay? And last but not least, I've got an input of 4 volts RMS going through a low-pass filter, and the output voltage drops minus 3 dBs. They didn't tell me how many volts it dropped. They told me how many dBs. Well, if that's the case, I've got to take the dB equation, which is right here, and I've got to do this thing that most of you, I can almost guarantee, don't remember. I'm going to have to take the inverse log of both sides because I need to try and get rid of this log function right here. The log function is slayed by the inverse log function to produce the ratio, to extract, to spit out the ratio away from the log function. You can't divide it out of the log. You can't multiply it. You've got to inverse log the function. Now, when you do that, you have to do that on the other side. Thankfully, we've got a number for this. It's minus 3 over 20. We take the inverse log. If you don't have a log to the minus 1 key, use the 10 to the x key. So type 10 on your calculator and then put the arrow, the caret key on your TI-89, and then type in minus 3 over 20. And you got to make sure you put minus 3 over 20 in a bracket, and then you will get a number when you multiply by 4, okay, that gives you 2.831. Now, how do I know that's right? Because 4 volts, and when I lose minus 3 dBs, like is shown here in the blue circle, when I lose minus 3 dB, I only have 70% of 4 left. So 70% of 4 is 2.831.